We're going to spend some time right now talking a little bit about group theory. And I'll have a couple of other lectures coming up that will precede this, talking about little bit of the background and why symmetry is important in chemistry. But in the meantime, let's just start really where most texts start, which is talking about symmetry operations. So why symmetry? One piece that's kind of left out often is that, so the square of any molecular wave function, vibration or electronic, must remain unchanged when operated on by a symmetry operation. So let me suppose I have some symmetry operation. We'll just call this some symmetry operation M, and that suppose it's a rotation of the molecule back to a orientation that's indistinguishable from the prior one. So M psi is going to take psi to, I'll just leave this quickly, with either plus or minus psi, because psi squared must remain unchanged. And so before the transformation, if I compare psi before the transformation, after the transformation, so this is, we'll call this, so M psi initial is equal to psi final, and again, which is equal to plus or minus psi initial. So the symmetry operators comprise a series of operations that we can take advantage of to understand a lot of the properties of molecules. A number of things, infrared spectroscopy, well, for that matter, anything dealing with electronic states, absorption, spectroscopy, fluorescence, all sorts of things that are important, and optical rotation we'll see a little bit later. So all of these things turns out are important. Now, we're going to start talking about, so I mentioned group theory. And what does group theory mean? Basically, it's the theory of mathematical groups. And so a group is a collection of elements that are interrelated according to some set of rules or operations. For example, the set of all integers, positive and negative and zero, constitute a group when the operation is addition. Now, we'll often talk about the operation, we'll just say multiplication. But we can, although we often call it multiplication, we can define it in any way so long as the operation and the elements give us the properties of the group. So what do I mean by having a group? So some rules. So first off, the product of any two elements of a group must also be an element of the group. The group is complete. I can't take the members of the group and generate another member through some operations of the members of the group. So one element of the group must commute with all the others and leave them all, and leave them all unchanged. So if I were talking about real numbers and the operational multiplication, that number would be 1. That element would be 1. Multiply by 1, I get the same thing back. If it's integers and addition, that element is 0. Okay, the associative law must hold for elements of the group. That is, it doesn't matter if I take that A, B, C must be equal to A operating on B, C. Now, it is not necessarily true that the elements commute. In other words, it is not necessarily true that AB is equal to BA. We've seen that before. Every element must have a reciprocal, which is also an element of the group. In other words, it must have an element which, when I operate it onto the, given the operation I'm working with, when I operate it onto that element, I get we'll just call it the identity element. Okay, that would be 0 for, so reciprocal for a positive number would be a negative number if the operation is addition. You can imagine, okay, so the operation is addition, my numbers are integers, so the reciprocal of -2 is +2 because the two of them add together to get 0. Okay. And the big point then is that it turns out that the symmetry operations, the set of symmetry operations of a molecule, which leave it unchanged, constitute a mathematical group. And so we can use the properties of mathematical groups to learn something about the chemistry. Okay, so I just wanted to give some. So there are symmetry elements and symmetry operations. An element might be an axis of rotation. The operation is actual rotation around that axis. So different classes that are important for us will first off be actually not even call an element, but the first is the identity operator E. So E operated on a molecule just leaves it unchanged. With another element is a plane of symmetry. So if I have a plane of symmetry, then reflection through that plane, leaving the molecule unchanged, is a symmetry operation. The element is the plane, the operation is the actual reflection. Sometimes we talk about a center of symmetry. That's not quite correct. We should talk about a center of inversion. The molecule has inversion symmetry. That means that basically, if I think of x, y, every x, y, z going to minus x, minus y, minus z, everything reflects through the origin. The operation is inversion of all atoms through the center. The element is proper axis of rotation. One or more rotations are an axis, and we have C designates a rotational axis or operation, and then N would be the order of the axis. So, for example, if I have ammonia has a threefold axis that goes through the nitrogen. Finally, a little more difficult one is the improper axis. And that's one or more of, so we rotate followed by reflection of the plane perpendicular to the rotational axis. An example here would be a good example, methane. Okay, doesn't like this. We'll draw it up at the top here. So methane and now if I take this as my axis and my plane here, if I rotate, if I rotate by a quarter turn, I'm going to get and then now if I reflect through the plane, so this is a rotation, we'll give it the designation that it is C4. C, rotation, 4, fourfold axis. But then if I reflect it through the plane, I just take every atom back up again. And what do I have? I have the same geometry. Back again. So those are the symmetry operations and elements that we're going to need to concern ourselves with. I've highlighted these, drawn some figures. So this cube has, if you can imagine, has different colors and different faces, and you'll hopefully be able to see as we go through how that works. I've also labeled all the vertices. And so if I take the identity operator is trivial. I have to include it for completion. In fact, one would say that if I apply a operation and it's reciprocal, that has to be equivalent to the identity operation. So for instance, a reflection times reflection back again through the same plane gets me back to where I was. Inversion times inversion gives me E. So yeah, it just looks the same. Everything goes to where it had been before. Reflection. If I have a reflection plane bisecting the object, what happens is that everything switches back and forth across the plane. And we end up with this. Inversion, if I have my, whoops, I did not mean to do that. Okay, if I have my inversion point roughly here, and what that's going to do is take everything back across you get the idea. Again, it's going to take every point x, y, z is going to go to a minus x minus y minus z. And it looks a little bit like this again, just drawing a thing out representing what this looks like in space. A proper rotation, so proper as opposed to improper rotation. A proper rotation, I have an axis and I have to rotate around that axis, then it's just going to give me this. I'm just going to take the cube, I'm going to rotate it. Now I'm using cubes just to demonstrate because a cube has pretty high symmetry, but so for instance, there are other planes, many more planes that the cube has, and many more axes of rotation. Finally, and maybe conceptually the most difficult one to see is the improper. Okay. No, I didn't. Excuse me. Getting ahead of myself. Additional rotations. So, take a fourfold rotation we had previously. You can probably see if I operate it again, it's twofold rotation. If I apply a C4 again, it goes 3/4 of the way around. If I apply it 4 times, it gives me the same gives the same thing back again. And so it goes to E. So I'm going to give an example. Let's take benzene, and it has a C6 axis. So any rotation is a rotation by, so any rotation Cn is a rotation by 2 pi over n. So C6 is a rotation by 2 pi over 6 around the axis. If we perform subsequent rotations, so you notice the notation here, we have C6(1). Usually we just drop the 1 because it's understood. If I apply it twice, I'm going to use I'm squaring it because what is this? This is C3, which is equal to this is C6, giving me C6 squared, which is equal to C3. You can probably see that if I rotate 3 times around, that's taking me 180 degrees. So that's a C2 rotation. And again, if I get all the way up to the end, 6 rotations, I'm going to get E again. So all of these have to be members of the group because if I apply C6 twice to get C3. I need to have C3. It needs to be part of my group. C2 needs to be part of my group because it is generated by subsequent applications of C6. Okay. Now we get to improper rotations. So an improper rotation is a rotation and then a reflection, or a reflection and rotation. It's not the order. In this case, the order is not important. So first off, what I've done is I've rotated the molecule, and hopefully you can see that from this figure. I've taken everything is rotated around. And then now my next step is reflection through the plane. And you can see what I've done is now I've gone and swapped these two. So I've inverted, I've flipped it through the plane. Not rotated. I didn't rotate. I just took every item and I swapped them back and forth. Some mirror plane. And that constitutes an operation called S4. So S is an improper rotation. These will usually just sort of fall out of higher symmetry molecules. They're sort of hard to see until you start looking for them. If you have a molecule that only has this symmetry, it will usually be pretty straightforward to see. I would just give an example, real life example. So let's take ethane in its staggered conformation. So I've got this, if I look down the axis, I've got one carbon, another carbon. I've got on the front, I've got, looks like this. On the back. And you can probably see that if I look down that bond axis that I just drew, there's a threefold rotational symmetry there. So what I'm going to do is I'm going to rotate that molecule, and actually I see that I made a mistake here because it's going to be if I rotate it, I'm rotating it by sixfold, not threefold. And then I have the reflection through the plane. And so this is not a C3, this is a C6. Oh well. And what I've designated here is I'll be using some figures from WebMO, and they use to show a improper rotation. They'll use the green. So put the plane, and then the improper axis. Okay, I already showed this earlier for methane, just showing you that if I take this and rotate it, again, if I rotate along this axis here, if I rotate it fourfold, I'm going to have, now it's going to be coming up, and then this one's going back, this one's going to be coming out a little bit more and back, and then if I reflect through the plane, I'll be back to the original conformation. So now methane has many symmetry elements, but one of them is the improper axis S4. Something about multiplications and different axes for improper rotation. If I have an even order S, will generate, okay, so I get the original one, and then 2, 3, 4, etc. So if I take the improper rotation all the way around, as with any other element, I get E. If I have an S2 element, that's equivalent to inversion. I'll just leave that without proof. So any even application of sigma of a plane gives E, So if I do an improper rotation twice, it just gives me a regular rotation because I've gone through the plane and I've gone back up through again. So again, look at S6 and see the first one. I just get the improper rotation. But the second, if I apply it a second time, I get C3. The third time, I get S2, which is equal to I, and so on until the end. So I generate. So if I have a even order S axis, I will need to generate some of these additional elements here. So some general rules. So the product of two proper rotations must also be a proper rotation. So just look at multiplying these. The product of two reflections in planes A and B separated by an angle is the same as a rotation about an axis defined by the line of intersection. You need to think about that for a moment. But what it gives me, more importantly, is two planes. If I have two planes that intersect, there must be rotational operations. And this will lead us to what we call C and V groups. More about that. It's called Schoenflies notation. More about that later. The combination of a rotational axis and a plane containing it must give a whole bunch of other planes. So if I go back to benzene, benzene had that. C6, there are planes that include this axis. For instance, this one right here. Okay. And so there must be other planes, n such planes, and n being 6 in this case. So you can see that, okay, yeah, there's another one here, and bisecting here, and bisecting here. So the C6 axis is at the intersection of 6 different planes. That is, if there's one plane, then there must be other planes. All of this will become hopefully a little clearer as we start working with these. Okay. The product of two C2 operations intersect at an angle phi as rotation by 2 phi or on an angle perpendicular to the plane. All right, let's see if we can decode that. So if I have a CN axis and one perpendicular CN and C2 axis, here's my CN. Imagine that I have a C2 perpendicular to it. That's going to generate another set of C2 axes, which are all perpendicular to the axis. And think about it a little bit. Let's suppose that this is a C5 axis, principal axis. If I have one C2, well, now I need to take the molecule is the same if I rotate it 5-fold. Well, that means if I rotate it 5-fold, if I have a C, here's my C5. Draw this out here. Here's my C5. And if I've got a C2 that's perpendicular, well, if I rotate this 5-fold, that means this must have other 1, 2, 3, I got 4 of them rather than 5, you get the idea. You're going to have other axes that will be generated. Okay. An even proper rotational axis and a perpendicular reflection plane generate an inversion center. So and some of these is, again, you'll start to see these molecules. We'll look at different classes of molecules. If I have so here's my, looking at benzene again. And now there is a horizontal plane. And the two of those, if I have one and then the other, that means I have inversion symmetry. Just a conclusion. Which benzene does. If I take any point x, y, z, map it into minus x minus y minus z, have inversion. That's pretty much all we have about symmetry operations. We'll get into, in a little bit, we'll get into how these apply to molecules in the subsequent lectures.